Okay, this is going to start our unit on thermochemistry. So thermo is temperature, so we're going to be looking at how temperature affects reactions. Work is done when a force is used to move an object, and energy is the capacity for doing that work, or it's going to be supplying the heat. And heat, we're going to use the variable Q, is energy that transfers from one object to another because of the temperature difference between them. So when you pick up an ice cube, it feels cold because the heat is being transferred from your hand to the ice cube. And when you pick up a cup of hot coffee, it feels hot because the energy is being transferred from the cup of coffee to your hand. So we're going to define what we are focusing our attention on as the system. So if you are holding an ice cube and we are looking at the heat transfer into the ice cube would be the system, and then everything else would be the surroundings, therefore your hand would be the surroundings. So the goal of thermochemistry is to look at the flow of heat from the system to the surroundings or vice versa. And the law of conservation of energy states that in any chemical or physical process, energy is neither created nor destroyed. So it's always going to be accounted for either as work, stored energy, or heat. It's not just going to magically disappear or appear. Heat flow. If it flows into a system, you're going to have a positive Q value, and that is an endothermic process. It is absorbing heat while the surroundings are going to be cooling down. So the ice cube in your hand, the ice cube is absorbing the heat, your hand is cooling off. If it flows out of a system, it will have a negative Q value. So this is where you would have a cup of coffee. Heat's flowing out of the cup of coffee. That's going to be exothermic, and then the system would be losing heat to its surroundings. You could also use the ice cube here, making your hand the system. So the heat from your hand would be transferring into the ice cube. You're giving off heat. You're losing heat to your surroundings. You're losing heat to the ice cube. So specific heat is the amount of heat it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. This is similar to a calorie, but we're going to focus on specific heat here. And it's going to be the heat input divided by the mass of the substance times the temperature change. So we're going to get this equation, C, which is specific heat, is equal to Q, which is your heat input, divided by the mass, M, times the change in temperature, delta T. So Q is our heat. It's either going to be in joules or calories. M is mass. It needs to be in grams. T in temperature, we can leave it in Celsius for these. And then C, specific heat, is either going to be joule per gram degrees Celsius or calorie per gram degrees Celsius, depending on what your unit for Q is. Your delta T, change in temperature, is going to be the final temperature minus the initial temperature. So you need to keep that in mind in case you're solving for one of these T's. You're going to have to break it up and rearrange to get it by itself. If this is exothermic, remember to make your Q negative because your delta T would then be negative, and we need to keep a positive answer for our specific heat. So if heat is being released, make sure you give Q a negative sign. It's not necessarily a negative value, but we need to use that sign to indicate that heat is being released. So we have a piece of copper with a mass of 95.4 grams is going to increase from 25 degrees Celsius to 48 degrees Celsius when that piece of metal absorbs 849 joules of heat. And they want to know what is the specific heat of the metal. So specific heat is C equals Q over M delta T. And 95.4 grams is going to be our M. 25 degrees Celsius is a T, and that's going to be our TI, our T initial. 48 degrees Celsius is going to be our T final. And we have 849 joules. That's going to be our are solving for C here, we don't need to rearrange, we can just plug it in. So C is going to equal 849 joules divided by 95.4 grams times T final minus T initial. Make sure you watch your parentheses when you're doing this. Make sure the denominator is in its own set of parentheses there. So 849 divided by 95.4 times 48 minus 25. And looking for sig figs, you're going to want to keep it at 3. So you should get 0.387. And this is a derived unit, so you're going to have to keep each of the units that is here. So it is joule per gram degree Celsius is our unit for this specific heat.